Hello everyone, and welcome to class number 30 of Physics 218. Last time, we talked about general principles of quantum mechanics, and in particular, how we've seen them play out in our discussion of the infinite square well potential energy. We also talked a little bit about matters of the interpretation of quantum mechanics and what it might all mean. Today we're going to shift gears a little bit. We're going to start talking about a different potential energy, the finite square well. I'll talk a little bit about the physical setup that we're going to analyze, and a little bit about why this might be an interesting or worthwhile problem to study with some real-world applications. I'll talk through the general solution of the time-independent Schrodinger equation for this potential energy, and how and what boundary conditions one needs to apply. I'm probably going to save a bunch of the gory algebra for a bonus video, but then after we discuss sort of how to think about this, we'll turn our attention to thinking about the physical features of the solution. And this is something you will continue to explore by looking at a simulation in recitation on Thursday. So here's the setup for the finite potential well. Here's a picture. So we're going to consider a well of width little a. I'm following Townsend's notation here. It turns out to make the math a lot simpler if we choose the well to be symmetric about the origin. So that's what we're going to do. In the center of the well, between x equals minus a over 2 and a over 2, the potential energy is 0, just like we saw for the infinite square well. However, this time outside the well, we have the potential energy not being infinite, but rather having a finite value v sub naught. I've labeled these three regions 1, 2, and 3 here, just because that will help us when we organize our math later on. So region 2 is inside the well, regions 1 and 3 are outside. There's one more thing I should mention about what we're going to do today. Throughout, we are going to assume that the particle has an energy less than V naught. Let's think about what this means classically, right? You know from our discussion of potential energy graphs a week or two ago, that if I have a classical particle, and let's assume that it was in the well, if it has a total energy less than the potential energy V sub naught, it can never get outside the well, right? Getting outside the well would require the particle to have a negative kinetic energy, which it couldn't have. So this is the case where the particle is classically bound within the well. What we'll see is that the results of solving the time-independent Schrodinger equation under this assumption, we get what are called bound states. What we will be able to see in a few more classes is that if we assume the opposite, that the energy is greater than V naught, we get a different class of behavior, which is actually much more similar to the quantum-free particle we talked about a little while ago. So that we'll discuss probably next week when we think about scattering and tunneling situations. But here's the physical setup. But before we dive into the analysis of this, I want to say a few words about why this is a relevant problem for us to consider. So it turns out to be possible to artificially create situations where you have a finite square well-like potential energy using semiconductor nanostructures. I'm going to cut now to something on my computer that can draw this better than I can. So here's an example of how one can make something that can be modeled by a finite square well. So the idea is that you have these layers of some semiconductor. So if you imagine a situation I've sort of drawn schematically here, we have this middle layer of, it could be something like gallium arsenide, where your charge carriers are effectively free to move. This is a sheet that's essentially large horizontally compared to its thickness. So you can model this as essentially 1D, where the charges within this gallium arsenide layer are free to move horizontally, but are vertically confined by the thinness of my layer. And for solid state reasons that we're not going to get into, we can imagine them as needing a larger potential energy to penetrate the aluminum gallium arsenide outer layers. So it turns out that in this situation, it's effectively 1D vertically, and the allowed energies for the charge carriers are controlled by the layer thickness. Just like, as we'll see, the allowed energies will be controlled by the well width and also the height of the potential energy well for a finite square well. So one of the reasons this is an interesting thing to consider is that this kind of semiconductor structure turns out to be the basis of many lasers that are used in telecom, and perhaps the kinds of lasers that are being used to transmit the signals that are allowing you to watch this. So before we dive into the mathematical analysis of this potential energy, let me take a minute to remind you of the general approach we outlined for solving the time-independent Schrodinger equation. So our first step is going to be to write down the general form of the solution piecewise if necessary. This is the first example where we will have to work piecewise because we have sort of three different regions in each of which the potential energy is different. Let's start off by looking at region 2, which is similar to what we saw before for the infinite square well. Now, in region 2, the potential energy is 0, right? So the time-independent Schrodinger equation becomes d squared. And I'll just write it as psi rather than psi sub n for now to save a little bit of writing. Dx squared plus 0 equals E psi. And here, being a little sloppy, psi is just a function of x. This is the time, we're solving for stationary states or energy eigenfunctions here. Okay, well, you know what this is going to look like, right? So if I rearrange this a little bit, if I multiply both sides by 2m over h bar squared, we're going to get a familiar looking equation. Okay. So this is a differential equation you know how to solve. And let me just define a constant here. Right, so I'll just define this group of things, right, as k squared for reasons that will, I think, eventually become clear. So let me write that as equals k minus k squared with k defined as the square root of 2me over h bar. Now, you know what the solutions to this look like. This is the same kind of differential equation as you solved for the infinite square well. It's the harmonic oscillator equations with position instead of time. So there's several ways we could try to write this. We could work in terms of sines and cosines like we did for the infinite square well. But for mathematical convenience, it's going to happen to be easier here to work with sines and to work with complex exponentials. And that's what we'll do, although you could do it with sines and cosines also. So without further ado, right, we'll be able to write down the solution here in region 2 in a general way. So I'll just label this as psi sub region 2 of x. We'll write it in the most general way with two constants, so as e to the a times e to the I k x plus b e to the minus I kx. If you're uncertain, take a moment to plug this back into the differential equation here and convince yourself that this is in fact a solution. Our next step is to try to solve the time-independent Schrodinger equation outside the well. So I'm going to start by looking in region 3. And there we have the following. So we have the kinetic energy term as usual. But this time we now have a non-zero potential energy. So we have a term where the potential energy is a constant v sub 0. And that potential energy multiplies our wave function, right? And then we have equals E psi. So let's think about how to solve this. It might help to try to rearrange this in a form that's familiar, that's similar to what we did before. So what I'll try to do is I'll try to isolate the second derivative piece here. And what we'll do is I'll start by subtracting this over. So I have E minus V naught times psi from subtracting V naught psi from both sides. And that gives me here by my kinetic energy term. Once again, I'll try to get the second derivative all by itself by multiplying both sides by minus 2m over h bar squared. And so if I do that, I get d squared psi dx squared equals minus 2m over h bar squared e minus v naught psi. But here we've got to remember one of the main assumptions we made. Remember, we assumed that we're we have the particle with an energy that's small enough that it is classically confined to our well. Namely, we assumed that the energy was less than V naught. Under that assumption, right, then E minus V naught is actually going to be negative if we assume this. So I could actually make this a little bit easier to interpret by bringing the minus sign inside. So we have d squared psi dx squared equals 2m v naught minus e over h bar squared psi. So now this looks similar to what we had before, but with a twist. I'm going to just roll over to here so to try to use up my limited board space. So this gives us d squared psi dx squared, and I can write this now in terms of a positive definite constant, which I'm this time going to call kappa. So I'll distinguish my k's from kappas. Kappa I will always write with a little curlicue, as opposed to k with like a straight side. Kappa squared x. Psi, I'm sorry. That's a psi, not an x. Kappa squared psi with kappa defined as now the square root of 2m v naught minus e over h bar. Right. Again, our assumption that the particle has an energy less than v naught means that this is positive inside the square root, and kappa is pure real. Now, this is a little bit of a twist compared to what we saw for region 2. So I'm going to pose a clicker question where I want you to think about what the possible solutions to this differential equation in region 3 might be. So hopefully you had a chance to think about it, and hopefully you've convinced yourself that solutions to this diffie-q, well, when I have the second derivative of the wave function being some positive constant times by wave function, the solution this time is going to be in terms of real exponentials rather than complex exponentials. That is in fact the case. So we can write in the most in the most general way the wave function here in region 3 as the sum of something that goes like e to the kappa x and something that goes like e to the minus kappa x. And the constants I'm going to pick are capital G e to the kappa x plus d plus for reasons I'm going to just for consistency with Townsend, I'll pick d e to the minus kappa x there. Now the behavior in region 1 is going to be very similar. We end up with exactly the same differential equation as we got here in region 3. So we know that we're going to have a solution with the same mathematical form. However, I'm just going to write the solution in region 1 with a different set of constants because it could be different. So let me just draw an arrow so we know that's region 3. And I'll write the wave function for so in region 1 we have psi underscore 1 of x equals we'll use c e to the kappa x, whoops, it's an x, plus f. My marker writing is not going so well. Plus f, whoops, e to the minus kappa x. And let me draw an arrow. So from here over to here. So again, to recap, what we have is sort of two different things going on. Outside the well in regions 1 and 3, the general solution is in the form of real exponentials, whereas inside the well, here, the solution is in terms of complex exponentials. So we have right now 6 undetermined constants, A, B, C, F, G, and D, right? So the next step is to apply some boundary conditions that will help us determine what these constants have to be. So we have 6 undetermined A through A, B, C, D, E, A, B, C, D, F, and G. I've just avoided E because E is not, E looks like energy, and so we'll need to figure this out by applying boundary conditions.